Today we want to look at solving right triangles. We're going to start with the problem that we saw on quiz 4, where we have a plane flying along and it's being blown around by the wind. So what's going on here is that the plane is flying at a certain airspeed at a certain heading. So airspeed and heading are what the plane thinks it's doing. Not that the plane is actually thinking, it's what the plane says it is doing. But then the wind comes along and us standing on the ground see the plane doing something else. We see the plane's ground speed and its track. So airspeed and heading are the speed and the direction the plane thinks it's going. Ground speed and track are what we see happening to the plane when the wind goes along. If there is no wind, then airspeed and ground speed will be the same, heading and track will be the same. None of that matters. With this problem only exists so that we could play the solve right triangles game. That's why the direction of the wind, the heading of the wind, has to be so carefully calculated to make this problem work as a solving right triangle. So of all the stuff that's going on in this problem, we're looking for the right triangle. And so we pulled the right triangle out here. We see that airspeed of 200 and that perpendicular wind at 40. That's the contrived part of the problem. The wind is going perpendicular to the airspeed of the plane. So now that we've pulled out the right triangle, we know we're just solving a right triangle. What's something that we can find on this right triangle over here? I've got this theta over here. I don't have this angle labeled up here, but for this theta, what is 40 called? That's going to be opposites. And what's this 200? Adjacent. And so what's this up here? Hypotenuse. We've also got another angle up here, but there's an opposite and adjacent hypotenuse. What piece can we find that might even be relevant to the problem? First thing we might want to find is hypotenuse. I've got two sides of a triangle. Let's use the Pythagorean theorem and find the third side. So the opposite square, adjacent squared plus the opposite squared is the hypotenuse squared. We can use the Pythagorean theorem to find the hypotenuse. Whether that's something that we want to find for this particular problem, not relevant. It's something we can find, so let's find it and then go back and see if it matters. So adjacent is 200. Opposite is 40. And this is the hypotenuse squared. So I'm going to need to take the square root of the sum of 200 squared and 40 squared. I don't know why I'm writing this all in red. And then we'll just grab our calculating machines. And we just type it like we see it. The square roots of 200 squared plus 40 squared. So we got 203.96. We'll worry about where it has to round if we go back to the problem and find that is useful. So with this opposite, adjacent, and hypotenuse, what else can we find about this triangle that might be relevant? Theta. We could find theta. What could we use to find theta? What trig function? Inverse tangent. Which is our best choice? That was a trick question. Asking that right after inverse tangent was suggested makes you think that, oh, is inverse tangent not the best? But inverse tangent is best. Why is inverse tangent best? We have opposite and adjacent. That's given to us. The 40 and the 200 are given to us. This 203.96 is rounded. So it's not as good as the 40 and the 200. So, great. We'll use inverse tangent. So theta is tangent inverse of opposites over adjacent. That's 40, not 400. So we'll do a tangent inverse of opposite over adjacent. We could also use sine or cosine now that we have the hypotenuse, but we'd have to be careful with that because it's rounded information. If we round off the hypotenuse to 204, that might throw off our angles. It might not. It depends on where we round it. So for example, if I did sine inverse of opposite over hypotenuse, we'd be fine. This is because our hypotenuse is so close to the adjacent, so we don't have a lot of place to go wrong. If we did cosine inverse of adjacent over hypotenuse, now if we were rounding to the nearest 10th, I didn't have this on screen. There we go. So we can see that when we do sine inverse of opposites over hypotenuse with the hypotenuse rounded to 204, we have a different value, but the value doesn't change until the 1000th place. Still get 11.31, 11.31. But if I use the rounded 204 in a cosine, I end up with 11.4 or 11.36. I get a different value. Depending on where we're rounding, that would throw us off. Best choice is to use non-rounded information. So, are these numbers relevant to what we need to find? Let's go back to the quiz. Question 1 was the force problem. Okay. So in question 2, we want to find the ground speed of the plane in miles per hour. Round your answer to the nearest unit. So which of these are either of these values relevant to that problem? What is the ground speed in our right triangle? What is the ground speed in our right triangle? 203.96. It's the hypotenuse of our right triangle. So we'll say the ground speed is 204 because it said round to the nearest unit. The next problem asks for the track of the plane. That's the only thing left that we don't know in this particular problem that's labeled. We want the track of the plane. The heading of the plane is 75. That goes from north to the airspeed. The track goes from north to the ground speed. How are we going to take the 75 and the theta that we just found to figure out the track? What are we going to do with the 75 and this theta that we found to calculate the track? So the heading goes from north down to the airspeed. In between the airspeed and the ground speed is where we find theta. And then the track goes from the ground speed up to north. So 75 is the whole thing. And then the wind is reducing the heading. So we can get the track by taking the 75 and subtracting theta. So the track will be the heading 75 degrees minus theta. So I'll do the 75 minus 11.3 to get 63.7. I forgot where I said to round it, so let's go back and look. Round to the nearest tenth of a degree. So we'll take the track, to find the track, we'll take the 75-degree heading, and we'll subtract off the angle theta that we found. Any questions? The point of the problem was not to learn about flying airplanes. That would probably be much more interesting, although kind of a nightmare with like 40 people trying to learn to fly one plane. The point of the problem was to grab a right triangle and solve it, and then go back, use those answers to answer the question. Any questions? Comment? Snide remarks? How's everybody, okay? Everybody's like, oh, very sad. Or you're very happy because you're thinking about Monday being a holiday, and this class only meeting 2 times a week. So like next week, the class only meets 1 time per week. Oh, awesome. I only have 2 hours each talking about. Right. So these are new quizzes that you can work on, quiz 3 and quiz 4. You can work on these, they'll be due next week. Like this cabinet here has almost enough space for the stuff, but not quite. Note that in this problem, the problem was set up with a heading. And so we had to figure out what heading was. For heading, it's a specific way of defining a particular angle. So we want to drop this back in and take our angles and move them out of acute triangles. That's our next big project. So our next big project, we want to start looking at angles and considering angles that are not sitting inside of right triangles. And then we still want to use right triangles to analyze what's going on. The tools that we have available right now are right triangles. Some of the angles, Pythagorean theorem, trig ratios. So we still want to use right triangles, but we're going to look for right triangles outside of just right triangles. So we're finding right triangles outside of right triangles. We're doing this because we've developed a tool set for dealing with right triangles. So we're going to look for right triangles in the problems that show up. Right now we have a hammer, so our job is to look at all the problems and figure out where the nail is. That's all we got. Later on, we'll add some more tools to the toolbox. But for right now, look for the right triangles because we have a hammer. I mean, look for the nails because we have a hammer. Let's define angles in standard position on Cartesian coordinates. We want to define angles in standard position in rectangular coordinates. So rectangular coordinates is going to be an X and Y coordinates. Our X is going to be horizontal. Here's a set of rectangular coordinates. Here's how we're going to define standard position. In standard position, the initial side of the angle is always the positive x-axis. So here's the initial side. The initial side of the angle is on the positive x-axis. And counterclockwise will be positive angles. We've got counterclockwise, we've got clockwise. We had to pick one of them to be the positive direction, and we decided that counterclockwise would be the positive direction. Go into the first quadrant first. So the way I indicate that is I say, going around this way is the positive direction. So if I've got an angle that ends in the second quadrant like this, we measured from the positive x-axis. We measure positive direction would be counterclockwise to the terminal side. Indicate that I put an arrow starting at the positive x-axis, going around to the terminal side, and there's theta. This is where we're going to have angles in standard position. So what angle do we have at the x-axis down here? How far are we? How far around have we gone? How many degrees? No, this one looks like it's about 135. But what is, if I just have an angle here at the x, if theta is sitting on the x-axis, how big of an angle is that? 0. How about the positive y-axis? What angle is up there? 90, because it's a right angle. And if we go all the way around to the negative x-axis, how big is the angle? And then down here at the negative y-axis, and back at the beginning, and then up at the top. Whoa, you're not supposed to go past 360. We can go past 360, we just end up at the same place. We'll be at 360 plus 90, which is 450. Thank you. I can't do everything very well. Theta equals 450 is at the same place as theta equals 90. So we only need to understand from 0 degrees to 90 degrees to 180 degrees to 270 degrees to 360 degrees. Once we figure out what's going on from 0 to 360, we know what's going on outside after 360 and even before 0. Any questions? Now we're going to have to throw some right triangles in here so we can see where we're going to put theta. All right. Let's take a quick break so we can draw a big circle and then look at some important angles that we care about.